calorimetry, how to use one, as well as how to solve problems using them. Now, a calorimeter is any instrument that's used to specifically measure how much heat is lost or gained in a process or a reaction. And you're going to have the chance to actually do a little bit of a calorimetry lab if you're in honors. If you're in honors, you're going to have a chance to do a lab with a calorimeter where you're going to have a chance to measure exactly how much heat is lost and gained by a system, okay? So let me show you a calorimeter. Now, when I was in college, I did a calorimetry lab in my Gen Chem 1 class, and we used a very high-tech 2 styrofoam cups. One was the base, one was the lid. You just have to make sure it's an insulator, and styrofoam is a great insulator. Why do we want it to be an insulator? Because we're trying to measure exactly what's going on inside. We don't want heat to be escaping to the surroundings, the outside. We don't want heat to escape out of the system. So because of that, we try to use something that's really good at insulating. Now, you guys in your lab, honor students, have an amazing chance to use a calorimeter that's a little bit more high-tech than mine. So here it is right here. Instead of being 2 styrofoam cups, it's a plastic piece with styrofoam in the middle, and then here's your lovely, wonderful styrofoam lid. What you're going to do is you're going to actually put water and a metal inside here. You're going to drop that in, you're going to put the lid on it, and we hope that very little heat escapes. Then this thermometer actually acts as not only a thermometer where you can measure the temperature changes, but it also doubles as a stirrer. Yay! Now, in reality, this is a pretty good calorimeter, and if you do your lab well, you're going to get pretty good results. But there are much more better high-tech calorimeters than this. But what I want to tell you is what you're going to do in the lab is you're going to take some water, and you're going to put the water in here, and you're going to measure its temperature. Then we're going to drop hot metal inside. We're going to put the lid on, we're going to stir it around, and we're going to see what happens to the temperature. Now, if we put hot metal inside cold water, what do you think is going to happen to the temperature of the water? Yeah, it's going to increase, right? The hot metal is going to heat up the water. What will ultimately happen to the temperature of the metal? The temperature of the metal will decrease. And how long will it do that? It's going to do that until they both have the same temperature. So do you see how heat is transferring from the metal into the water? This is why we hope no heat is escaping. Because we can take that fact, wow, the heat is going from the metal to the water. Wouldn't it make sense for us to assume that the amount of heat that the metal loses equals the amount of heat that the water gains? This is how a calorimeter works. That's how it works. We can mathematically measure whatever we need to measure based on what our goal of our lab is. But you're definitely, honor students, going to have a chance to do that on your own. So here's our formula. The amount of heat lost equals the amount of heat gained. Now notice I have a negative number. I have a negative right here. Why? Because remember that when you lose heat, that's a negative. And when you gain heat, that's a positive. So we need to make sure that we don't end up with a negative mass or a negative specific heat. We need to make sure that our numbers work out. So we just have to make one side negative. It does not matter which side you make negative. Honestly, I usually put the negative over here because I don't like dealing with negative numbers. So I like to make the lost side, since that side's already negative, because you're losing heat. That's a negative joules, whereas when you gain heat, that's a positive joules. So I usually put the negative sign on the side that's already negative. You just need to remember, put the negative somewhere, okay? So if Q, if we're talking about temperature changes, we're not talking about any phase changes. As we're talking about temperature changes, that means Q is mc delta T, mass times the specific heat times the change in temperature, equals the amount of heat gained by the water, mc delta T. So we have two different substances going on here. So let's go ahead and see if we can figure out what's going on. Okay, so use my blue marker. Okay, so let's read through this problem. A 20-gram piece of metal at a temperature of 90 degrees Celsius is dropped into an insulated container holding 125 grams of water at 20 degrees Celsius. If the final temperature is 23 degrees Celsius, what is the specific heat of the metal? So here's what we're trying to find. The specific heat of the metal. And actually in your lab, this is what you're going to be doing too, honors folks. Now, since we've got a lot of numbers, my suggestion is that you split this up based on our two substances. We've got metal and we've got water. And all of our data, we've got mass, we've got specific heat, we have final temperature, we have initial temperature, and when you subtract those, that's going to give us the change in temperature. Okay? So, a 20-gram piece of metal, ooh, there's our mass of the metal. At a temperature of 90, there's our initial temperature of the metal, is dropped in an insulated container holding 125 grams of water. There's our mass of the water. At 20 degrees Celsius, there's our initial temperature of the water. If the final temperature is 23, now, that's the final temperature of which? Do you remember heat's going to continually being transferred until they're the same temperature? Because heat moves from hot to cold. It's going to continually transfer until they're the same. So that's actually our final temperature of both. Okay. Our specific heat, we're talking about liquid water. That's 4.18 joules per gram degrees Celsius. Remember, I want to see units in your work. If you list them here, then you don't have to write them off to the side. If you don't want to list your units here, then you've got to make sure you show them in your work, okay? When we subtract these, we get 23 minus 20, that's 3.0 degrees Celsius. Do you see how we lost a sig fig here? Tenths, tenths, tenths. So now, our final answer actually should have 2 sig figs, guys. Final answer should have 2 sig figs. Why? Because of this. When we subtract, we don't look at number of sig figs, we look at placement. And that should be to the tenths. Okay. Now, this is what we're trying to find, specific heat of the metal. And let's subtract these. We get a negative 67.0 degrees Celsius. Okay, so now we have all of our numbers. Let's just plug this in. Q lost equals negative Q gained. So MC delta T equals MC delta T. Do you remember how one side needs to be made negative? Why? Because we have a negative temperature right here. The metal side's going to end up being negative, the water side's going to end up being positive, and if you don't change something, you might end up with a negative specific heat. Well, you definitely won't end up with the right specific heat, that's for sure. So, let's plug and chuck. 20 times the specific heat of the metal, that's what we're trying to find, times the delta T for the metal is negative 67. Equals the mass of the water, 125, times specific heat of the water, 4.18, times the change in temperature, 3.0. So if you look, that's why we've got 2 sig figs in our final answer. Now, do you see how we have a negative over here and a positive over here? This is the side I usually choose to put my negative. Why? Because 2 negatives cancel each other out, and now we get to deal with positive numbers, whoop, whoop, which I like better. Okay, so now we just need to divide. We've got to divide by 20 and divide by 67 to solve for this. Okay, that cancels these out. Divided by 20, divided by 67. So we end up with C equaling 125 times 4.18 times 3 divided by 20 divided by 67. And when I do that, I get 0.39. And we have to watch our units, joules per gram, degrees Celsius. If you forget the unit for specific heat, It is on your reference tables, so don't forget that. It is on your reference tables. We look for specific heat. It says joules per gram degree Celsius. There's no reason why we should miss that unit. There's your answer. Now, more than likely, it's going to ask you to go and figure out what metal this is. So pull out your reference tables. Find on the very front where it talks about all the metals on here. I mean, it's obviously not all of them. And then we look through and we find the one that's closest. Hey, zinc is 0.388. That's really close. That's pretty good. I would be so excited if this were my data. So we can be pretty confident. This is really pretty close. Very low percent error. So that's looking like this metal's probably zinc. There you go. So here's how you complete the calorimetry problems.